Okay, good morning, everyone. I'm very happy to be with you here today. We can finally share what we've been working on for the most part of the year by now, which is about introducing Parquet into the Prometheus ecosystem to see if we can handle long-term Prometheus data with it. But before all that, let's introduce ourselves. My name is Jesus Vazquez. I'm a senior software engineer at Grafana, and I am joined by Michael Hoffmann, senior software engineer at Cloudflare, and Alan Protasio, senior software engineer at Amazon. What brought us here? Well, the three of us are maintainers of three different downstream projects of Prometheus, Cortex, Mimir, and Thanos. When I first joined the community, I remember watching a talk where they were sharing that Thanos was influencing Cortex with ideas and vice versa, and I'm happy that that continues to happen today. Throughout our experience running and maintaining clusters of these technologies, we've all experienced similar pains on the query path. More on that later. But perhaps the thing that inspired us to work on this and talk about this today here is this talk about Philip Petkowski, which did this awesome work at Shopify, where he modified Thanos queries to use Parquet. So that talk happened around November last year. And unfortunately, the code is not open source, but the contents of the talk were great. And we didn't know at the time, but we were all working on this separately. And in my case, it wasn't until March this year where I used one of the hackathon that we have at Grafana to kind of work on this a little bit. And I joined Grajo and a few others in the company to fork Prometheus and see where we could fit Parquet inside it. That same week, someone told me, I believe it was Gotham, that Cloudflare had open sourced a repository where they were trying to do a similar thing that Philip did. And so I immediately reached out to Michael, and I created this CNCF Slack channel, Prometheus Parquet Dev, and I went to sleep. And the day after, people from Red Hat, Reddit, and Amazon showed up on the channel. And that's when we met Alan, and he also said he was running a POC internally. So the next step was clear for us. We had to join forces, and we created Parquet Common, which is a library that exists in the Prometheus community organization. It passes 100% of the PromQL acceptance tests, so any sort of PromQL query should run. The library is low level, it's meant to read and write Parquet files, but we thought it would be useful for people interacting with it to have like a queryable implementation, Prometheus interface. So you can just generate a set of cities and run a Prometheus query against them. So that's useful. Then all the downstream projects will have their own implementations, but yeah, this is good for the library. And other things it includes, it's able to generate Parquet files from a set of cities, and it can also convert TSDB blocks to what we call Parquet blocks. We've got great progress since April. We've got like 90% better, 80% faster, 90% less get range calls, 70% less memory usage, and 40% less allocations. But these are benchmarks against the library itself, not against Prometheus. So this is just how it's improved overall. Right, so why are we doing this? I'm pretty sure people in the room have experience running or using Mimir, Cortex, and Thanos, and perhaps others. But in the case of these three, you're probably familiar with the component store gateways, which has a lot of state. It's a stateful component. It has to pull the indexes of all the blocks to resolve the queries against long-term data. And over time, at certain scale, this component starts to get big disks, and these disks become expensive. And also, when you add a new pod to your replica set, it takes time. We have customers taking up to 50 minutes or half an hour to sync a single pod. So this also becomes an availability risk, because if the pod goes down, you lose access to query that part of the data. And to make up for that, you typically add more zones or over-provision the pods to make sure that this doesn't happen. So overall, it's an operational challenge to run, and you're typically bleeding a bit of money here. Another thing is that if we assume fixed retention, like 12 months, data is only increasing because people is instrumenting more and more. So these problems are not going away. If anything, they're getting worse. And then more motivation, we also wanted to, we were thinking, we know the limits Prometheus has with high cardinality, so we were thinking if there is a format that perhaps can help us handle better cardinality, because the index grows a lot with high cardinality or high dimensionality, more labels. we will win in that front as well. And as we learned from the talks on OTel, we know that the OTel spec is still evolving with the resource attributes, with the entities model. We know that Prometheus has its issues with it. So perhaps if we had a more flexible storage. Of course, there's a lot of work to be done in the Prometheus itself, like what's a resource in Prometheus. There's no struct saying what it is. But if the storage was more flexible, I think it will be great. And last but not least, we also wanted to explore. We've seen in the ecosystem people playing with columnar store and getting good results. So we wanted to see for ourselves. So now I leave you with Michael. He will explain how the TSDB index works and what are the problems we see in the store gateways when we query long-term data.
Yeah, so is the microphone working? Yes? Okay, cool. Let's explore why we think that the TSDB index kind of gets into our way at times. And let's do that by working through an example select call from the select call for some vector matcher to the final materialized series set, while keeping track of the consecutive read operations that the time series DB index forces us into. So given some vector selector and assume for simplicity just one equal matcher, the first thing we have to do, and I don't count this as a read necessarily because that's highly amortized, we have to look up postings for it, and to know where those postings are stored in the index, we have to know the offset for the postings that match this particular equal matcher. I read that from the postings offset table by section. It's sorted. That's quick. That's nice. And before my first read, I will read the postings list from the index. Postings list is the set of series IDs that correspond to series that match this equality matcher. So first read. I do that for all matchers. I intersect the series, the postings lists, and that leaves me, in this example at least, with one series with ID 23. That's great. I have all the series that match my query, but I cannot yet hand that to the query engine. I need to materialize time series data and labels still, so we are not yet done. The series IDs also function as offsets into the series table if I multiply them by 16. So I now know where to start reading data in the series table, but I kind of don't know yet where to end reading data. Right? I only have the offset where it starts, but it could be arbitrarily long. So the second read I need to do is read an integer at that offset to get to that. That tells me how much data I need to read subsequently to get all of the series data for this time series. I do that. That's my third read, and end up with all of the label key value pairs for that series and some chunk metadata. No chunks yet, only metadata. This chunk metadata contains chunk references, which again are offsets that I can follow into a chunk file to read the actual time series data that's stored there. But again, it doesn't tell me where to end reading. So I go to the offset, read an integer that tells me how much data to read next. And finally, I do one last read for that size at that offset, and I end up with sweet time series data. I mash it together with the labels and build a series set and return it to the query engine. So if I counted right, that's 5 consecutive read operations I need to do to get from vector selector to series set. That kind of works okay for Prometheus if I have local fast disks and a memory mapped index. It got us this far. Prometheus works well. But as soon as I try to do the same thing on object storage, things get less nice, because object storage generally, I would say, has a pretty high time to first byte, at least compared to disks, and okay throughput. But we're not using any of the strengths, and we're paying for all of the weaknesses here. These happened before edges that the index forces us into, makes us pay the time to first byte that's relatively high sequentially, which is not great. And the time series database index stores data ordered in classic series order, lexicographically by its labels. But that's not necessarily how I want to read the data, right? Maybe consider being Cloudflare and you operate a federated Prometheus that pulls data from all of our edge network, disambiguated by like data center ID and maybe a region label. And now if I want to query that, let's say application CPU usage, there might be an application name label that lexicographically comes before data center, right? And if application name is sufficiently high cardinality, then the series that correspond to like one data center gets shredded by that cardinality into essentially random lookups in a large part of the index file. So I cannot even take advantage of like throughput because I have to do many small reads. Sorry, and that's not great. And what else? Yeah, finally, that's a very naive way of doing things. Of course, a real production storage gateway does not really do those 5 reads. There are plenty of caches and heuristics involved. But I think the point I want to make is that time series database index does not really help us here. We need to be clever. We need to come up with caching strategies to kind of make it work. And heuristics can break and caches can be called, right? So I do pay for this with high P99 latencies and with high startup times because I need to memorize maybe the postings offset table on disk and download it if I start a new object gateway. So I hope all of you are now sufficiently scared of index files and object storage, but don't worry, we think we have a better way. Why instead of storing data in a way that I have to access it through consecutive, essentially map lookups, we just store it in a flat table and in some columnar format. In our case, we chose Parquet, but that kind of does not matter. But we store it in a flat table. And Alan will walk you through in a minute how to actually read that data in Parquet format, but let me quickly introduce the schema we came up with. That's essentially the first thing you would do if you would write your data in a table. Every row contains one time series. Every column corresponds to a label name. We do shard our data into blocks horizontally, one of length 1. And we have 3 data columns that contain also the chunk data, but are sharded into 8-hour ranges to have some balance between. Because if I shard it in 8-hour ranges, the smallest amount of data I can read is 8 hours. So there is a balance between a read query, a range query that I can schedule reads concurrently for 8 hours, and like an instant query where I have to overfetch 8 hours. But in practice, it works fairly well. And that's it. It's a fairly simple schema, but it already helps a ton. And yeah, Alan, why don't you walk us through a time series lookup?
Yep. Is it working? Thank you, Michael. So yeah, let's try to do the same exercise that Michael did to walk step by step in how we are fetching the data on the Parquet files. But a little bit before that, let's talk in a very high level how the Parquet file is, the layout of a Parquet file, and also some concepts that we'll be using. So this is how we store the data in a Parquet file. The first thing that we can see is called row groups. If you think that your data is you visualize your data as a table that has rows. In our case, each row is a time series. A row group is basically a partition, a horizontal partition of your data. So when you're writing the Parquet file, you can say, look, my row group size maximal is 1 million. So every 1 million rows, the writer will create a new row group, and you start creating the same structure over and over again. Inside each row group, we have like an optional Bloom filter that is an option in the common library that Jesus talked about. So it's the first bytes will be like Bloom filters for every column or the columns that you choose to create. And then you have the column chunks. So for each column in your schema, you have the chunks. It's a columnar format, so like the data will be written by column. And inside of each column chunk, you have the page. So the page is like the minimum amount of data that you can read in the Parquet file. Data inside of the page is compressed together and encoded together. Depending how you are encoding your column, you can have different types of pages as well. Let's say if you are doing a dictionary encoding, the first page is a dictionary, and the remaining page will be reference to that dictionary, and so on and so forth. So we have this structure, and then we have multiple row groups, and at the end of the file, you have the footer. In the footer, you have metadata about the file, like how is the schema, the number of row groups, the statistics of each row group, and all like number of rows in general. And we have like three things that we'll be using to run a query. The row group statistics are like row group index, the page index, and the offset index. We're gonna go one by one in the next slides. So let's say that you have like this from QL, very simple, like pre-matchers or predicates or constraints, whatever you wanna call. We have metric name, container CPU usage, container DB Postgres, and namespace cache. So the first thing that we do is like in a single call, we fetch the footer of the Parquet file. In the footer of the Parquet file, we have the row group statistics. This information will have like the min and max. Oh, sorry. You have the min and max of every column and row group in that row group. And then you can use that information to start pruning row groups. So let's say for the first matcher, using that information, I know that I may have data in row group 1 and 2. And then I do the second matcher. I have maybe information in the row group 0 and 1. And I do the third one. So at that point, I can prune all the row groups that is in a PromQL is an end constraint. So I can only get the intersection. So at that point, I know that like the only row group that I need to open is row group 1. So you do a very similar thing now inside of the pages of the row group 1. You have the page index, you have the same information. For every page, you have the min and max of every column. So you do the same thing. Like you do like metric name equals container CPU, whatever. Then you do the second one, the third one, and now you have like, okay, I know that I need to open the row group 1 and the page 1 of the row group 1. I do all of this just looking at the footer of the Parquet file. Then now there is no other way. I really need to materialize that columns to filter out the rows that I'm interested in. So to do that, I use another thing in the footer called like offset index. So in that index, I have like the page location, so like where this page is located in the Parquet file. So I know that I'm doing 3 constraints or 3 matchers. I need to download those 3 columns, that page for those 3 columns. I do that. Now I have all the rows for that page. And then I apply the filters like container CPU, like all the rows match. And then I apply. And then I say like, at that point, I know exactly what series I need to fetch that match that PromQL. At that point, I finish my index lookup, what we would call in the TSDB. And now I only need to fetch the samples. For that, I go to the second Parquet file that we call chunks. We do the same thing. We found the page for that rows, like these 2 Parquet files has a 1-to-1 relation. So I find the page for the respective time series. I find the locations, and I download all the pages that I need to fetch the samples. There's 2 things that's interesting here. Like the first one is that like before doing any call, I have like all the locations that I need to fetch. So I can plan how I'm gonna issue my calls to the object store. So I have a way better way to like plan my access to object store, which has huge advantage. The second thing is that we do projections here. Like if this query has an aggregation, so I don't really need to materialize the extra labels for that series. So I just skip it. If we have like a by job clause like that, then I go and fetch the extra column that has the by clause, and then I give to the PromQL engine. At that point, we did everything that we needed. We hand over the data to the PromQL engine, and then PromQL engine like do the rest. That's basically it. It's a very simple flow. Like all the data is kind of partitioned. You are scoping down your query all the time, and we don't have like this global symbols table, and we don't have like the global postings that I have. I don't know, n equals to prod, and I have a huge posting lists and things like that. That's basically it for the fetching part. This is just like a comparison. This is a random block that we pick in some of the clusters. This block had like 13 million time series, I guess. And we can see like the chunks files, the sum of all the chunks is 26 gigs in this case. And like the chunks.parquet, which has the same data in the Parquet format, only have 14 gigs. It's a huge change in size, but it's even bigger in the index size. The index in this case had like almost 4.6 gigs, and the labels.parquet, which has the same data and is the file that we use to look up the series, has only 153 megas. That's basically it. We were going to do a demo, but your laptop is not.
But we have a screenshot.
Oh, I didn't update the. Let me connect it to the internet. Yes.
We took a safety screenshot of a demo before this happens. But if you want to see a live demo, just hit us up in the lobby at some point. I can show.
I need to refresh here.
It's same range, same data. On the left, Parquet. On the right, it's our productive Kubernetes setup, Thanos setup. It's 3.5 seconds on the left when read through Parquet format, and like 17 on the right. Much better. And that's a general picture. It's really much better.
And also no state.
Pardon?
No state.
Yeah, no state. They just start instantly. And that's like a day, I think. Yeah, that's just fetching data for 1 day. And I think it's some CPU usage for some namespace, some container, I don't know. That's it.
Questions?
All right.
Hello. Besides the great optimizations, do you see the Parquet files unlocking new features for Prometheus?
Yes. For example, the first one that comes to mind is metadata. In the design that we chose, we split already into 2 files. Well, like we can see that there. Well, over here. So we have 0 labels.parquet at the bottom, the bottom 2, and then the chunks. Metadata could be a separate file. And something that's been a problem in Prometheus has been making it retro backwards compatible. So every time we introduce something, we have to first introduce a change that's in case you revert to the previous version, nothing blows up. With Parquet, I think it will be easy because you just add a file that has a one-to-one relationship with the others. And if you go back a version, it doesn't know about the file, it doesn't open, it doesn't break. Yeah, so I think, yes, metadata, and I think it makes things easier as well. Yep.
Hi. Thanks for the amazing presentation and amazing optimizations. I was wondering about the query materialization. So is it possible to, like when you're writing a query, to like just fetch up until like the label pages, just so you can have a count of amount of way before you execute? Is that something that you've thought about?
That's how we implement limits, right? As soon as you're done with this cascading filter, you know exactly how many rows, you know exactly the byte ranges, so you can sum up to how much data you would need to fetch, and you can implement really sharp limits on like the amount of rows, time series, and the amount of bytes that you want to download. That's actually done in the library.
Yeah, that would be really good for like limiting really bad queries.
Yeah, you know everything in front of doing any.
There are already limits, right?
Pardon?
Is there already
Yeah,
some
yeah.
limit?
Yes,
Oh, there's
Implemented.
pretty. Yeah,
we have some.
that's
Very bare minimum, but
okay. Thank you.
Hi. Oh yeah. My
You can go. Oh. Is it not green? Okay. Can you?
Hi. My question is more towards the implementation path. I'm also using Thanos, as in my S3 bucket doesn't have that amount of data what you at Cloudflare might have. But in general, how do you proceed? Let's say this goes live and I want to use Parquet files now. So do I do like an initial migration of the existing objects on the S3, and that kind of look like?
so the library has a package called Converter, I think. What we've done, the 3 projects have a version of this, not the same, but very similar. We have another service called the Converter. And so the Converter looks for the blocks that are on object storage and generate the Parquet files. And you need to make a few changes, but then your queryers know which blocks are have Parquet data, which don't, and use one engine or the other based on that.
Okay, so over the period of time, I would clean it up, right?
Yeah. So you start converting today,
Yeah.
and over time you could convert backwards if you want, but that's a lot of work.
Yeah.
But over time, if you wait a year, you will be migrated. Yeah.
And specifically for Thanos, there's a Thanos community project called Parquet Gateway that implements series and query RPC, and you can just point your query at it, and that should work. I personally configure it with the distributed query engine. That's
Okay. And do you see this benefit only for, let's say, companies or consumers who have big stores? Or let's say on S3, I have 1 terabyte data. Would it make a big benefit for me? Have you done that kind of a comparison? As in, switching would also take time, as you told.
I mean, in the end, you will store less data, as you see, it's
Yeah.
more compressed, and you do less lookups. And maybe you don't face issues where your storage gateway starts for an hour, right? But you still save on requests to object storage.
Okay, thank you.
One quick question over here to your left. The metadata in the footer, is that like a convention with Parquet files, or
Yeah, it's part of Parquet.
so you always store it at the end in Parquet?
Yeah.
No, like it's just
Yeah, when you open a Parquet file, what you're actually doing is reading the footer. And then you say, I want to read 10 rows. And you resolve
it's not
the
a
offsets, and you read.
seems like it would be classically a header. I'm just confused by the naming, I guess.
Yeah, it's not a header, it's a footer.
Yeah.
But it's the same.
I guess because they write after you are writing the code, all the rows and the row groups, and at the end they write the footer.
Yeah, you keep track of the min-max.
Probably they put the reference of the footer in the beginning of the file, so you know exactly where to read.
Okay, really amazing work. Thank you for joining forces together. I think every user wants to have one project that do those things. Now we have sort of kind of combined work together. My question is like from the user perspective. We have Cortex users, Thanos users, Mimir users. Do you see this thing to be really a default very soon? And what people can, when they cannot adopt it, when can use it? Like how they can help maybe to make this happen? Like what's the next step?
It's a bit tricky. I don't know the full answer to that. We are at the stage where all of us are testing this at scale and fixing things. And then I guess we need to have a conversation on whether do we want to adopt this in Prometheus or not, or is there a way that Prometheus can say how to interact with it with Parquet, like a formal, so that users can rely on this and make a decision?
On Cortex is already experimental feature, so you can deploy.
Good luck.
Thank you again. That was amazing work.